So now I just want to share my screen and I want this document to start with. Okay. Let me just toss that across. Oh, that stupid transcription. Hang on. I'm going to. There we go. Turn that transcription off. That's annoying. Okay. So starting off with from the so this document that I've got here, that's on our OLE page there. So there's two documents that I've put. One's called Scholarship Revision and one's called Revision Examples. And I can actually just drop that into the chat here too, actually. Let me do that. And drop those in. Okay, so I've dropped both of those docs into the chat there as well, so that you can type on or whatever else as we go. So any other bits and pieces that occur to you, you can add to your own document. So we know that the exam generally has 5 questions, and those 5 questions, 4 of them are usually about the data, about analysing data, and one of them is about the probability stuff. So I'll start with going through the data section, and then I've got another chunk of stuff at the end, which is about the probability, because I know we didn't quite get through all the probability stuff that we wanted to do earlier because of lockdown. Yay for lockdown. So start with experiments. So the key thing that when we look for experiments is we are looking for that allocation. In fact, the key word there is that it needs to be a random allocation. So when I look through any paragraph that they give us with info, that's what I'm looking for, that they've told me that it's been randomly allocated. Now, when we have our control group and our treatment group, the key thing is that we're either looking for that placebo. Now, do you girls know what I mean by placebo?
Yes. Yeah.
So that placebo would be the sugar pill, if it was in a pill form, or if it was doing a vaccine, then that would be a saline vaccine. So it's something that's completely neutral, that isn't actually doing anything, having an effect. So it can be that, or it could be a standard treatment. Then we need to control all of our conditions, except for the one that we are testing. So that's when we look at controlling the variation, making sure that the temperature of the room is the same, that we're using the same pens when we write, any of those kind of things. Blinding, we've got our single and our double blinding. And there are times when we can't do any blinding, depending on the experiment. And then the other part is our replication. So when we repeat the measures. So when we look at the results that we get, we talk about cause and effect, or causation. Doing this causes this to happen. This is the effect that it has. And in particular, we look at the randomization test to compare with chance alone. So I'm just going to flick across to the other document. And so what I've got here is I've got some couple of experiments that were done, and we'll just have a look through what the results look like, how we would interpret and analyze those, and what conclusions we draw using some of those ideas. So this is an experiment that was done, and I had a group of students, and they had to stand either on their dominant leg or their non-dominant leg and see how long it could take them to do it. So my first question is to think about, well, what would my treatment and control groups be? So I've got these two groups, dominant and non-dominant. Which one would be the control group, and why? So think about control group has to either be a placebo or whatever the standard or the normal thing is. So then my question is, standing on your dominant leg or standing on your non-dominant leg, which of those is the normal thing to do?
Dominant
Dominantly.
Good. So that will be our control group. So our control group is the dominant leg, and that's because that is the normal thing to do. And therefore our treatment group will be the non-dominant leg. So what I also want to think about is, what are we testing the effect of? What is the cause and effect that we have going on here? So think about what we're measuring. So the axis there, we're talking about the time that it takes them they can stand on that leg. And that's looking at how many seconds they can stand on that particular leg for. So what is it that we would be testing for? Any ideas? So have a think about, we know our response variable in this case will be the time to stand on one leg. And if I think about what the cause and effect issue would be talking about which leg you're standing on. Does that cause there to be a difference in the time you can stand on that leg? Okay, so when either you're standing on your dominant or your non-dominant leg, does that cause a difference in the length of time it takes? Does standing on non-dominant leg cause a difference in the amount of time? And that's when my hypothesis would be that, yes, I think there should be a difference because I expect that their dominant leg would be stronger. And then I could talk about why that would be stronger and that would back up my hypothesis. Is that okay?
Yes. Yeah.
Cool. So the second part then is looking at the features of the graph. And so when we talk about this kind of graph, it's very, very similar to, or it's exactly the same as the normal dot plot box and whisker graph that we want to talk about, shape, center, spread. So those features are the same whether we talk about experiments or whether we talk about inferences. The graph is still the same that we refer to. So what can you tell me about the shape of the dominant leg? It's harder when you've got small numbers of data. Can we say that our dominant leg is definitely normal or left skewed, right skewed? Okay, so another little trick to remember is if I look at for example, the box and whisker graph, and I'm going to look at the non-dominant one first. If I compare where the center of that is there, and I look at how spread out the data is to the left and to the right of that, is it pretty evenly spread on both sides?
No.
So which side is more spread out?
The right.
So that means this is going to be right skewed. And I can see that a little bit with the dot plot, that I've got a lot of data on the left and then it's more spread out on the right. But now I can use that same idea with my dominant group. If I look at that box plot and look where the median is and think, right, what's the distance on the right-hand side versus the left-hand side? Are they about the same, or have we got skewed data?
Slightly skewed.
And will we say left or right skewed? So the
Right
long
skewed.
tail is on the
On the right.
right. So that's going to make it into a right skewed. Is that okay? So if we can't see it well from the shape of the dots, go back to that dot plot, the box plot, and use that idea of from the median, is it symmetrical on both sides or not? So in terms of my features there, and when you're in the exam, you just want to write down kind of bullet points idea that you do it quickly, but get the main ideas across, and you don't need to stress about like in internals when you had to write lots and lots of detail. So I can say dominant leg times, in fact, it's both, and non-dominant leg times right skewed. So that's my shape. Shape. Then I also want to talk about center. Now, when I compare the center, what statistic do we look for? Look at our means and our medians. In this case, which one is the more accurate measure of center? Should I be using the mean or the median, and why?
Median.
Because
Mean it can get skewed by large or small numbers.
Good. So because we've got data that is skewed, that means that the mean is not the best measure to use, because the mean is going to be affected by those that tail, those outliers. So we want to compare the center. Sorry, compare the median, not mean, as it is skewed data. And so when we want to compare those medians, we can say, well, the first one, we've got a median there of 51 seconds and 115.5 seconds. So which one is students standing longer for? Are they standing longer on their dominant or their non-dominant leg?
Dominant.
Good. So we can say that the students stand for longer on their dominant leg, and then I want to find the difference between those medians. So that is going to be, grab my trusty calculator, 64.5 seconds. So that's all I want to say, is that the median time standing on dominant leg is 64.5 seconds longer than the non-dominant leg. Okay, and then spread. Two ways that I could measure spread. One of them is our standard deviation. So I could look at those SD, standard deviations there, or I could look and compare the width of the box, which is our interquartile range. Okay, so I can either calculate the IQR and compare the IQRs, or I could compare the standard deviations. Which of those is the best one to use here? If we've got right skewed data, which one's more stable? We're going to go with our interquartile range. Yep. So we're going to go with the interquartile range because that is more stable when we have skew data. Okay, if we had a lovely normal distribution, so think about, for those of you that have been doing the normal distribution and probabilities and stuff, because it's normal as a beautiful symmetric distribution, that's when we're allowed to use our mean and our standard deviation. And as soon as it's not, then the interquartile range and medians are much better. So if I look at those two boxes, which one's wider, the dominant or non-dominant?
Dominant.
Dominant.
So we can talk about how the spread of the dominant times is more than the non-dominant times. So I can say the spread of times for dominant leg is more than non-dominant. And calculate the interquartile ranges, and we just got to remember that's upper quartile minus lower quartile. Okay, so that's when we just go and find those statistics here, and there's our upper quartile and our lower quartiles, and we would just subtract those to find the difference. I'll leave you guys to fill that one in a later stage. The key thing is that we've done a comparison and written that up very quickly. Cool. So that's our features, shape, center, spread. But now we get to the conclusion side of it. Okay. And so what we have here, this is called a randomization distribution. So it's a bit like the bootstrap distribution, where they do some resampling, and that's why I've got so much data down here. And you can see there they've actually got a sample size of 1,000 because they've done 1,000 randomly allocating participants into groups to test out how much evidence have we've got. So the key thing with the experiment is we want to compare the results to random chance. So we want to say, well, how likely is it? So this difference that we got here of 64.5, and you'll see there's my 64.5, that's that difference in the medians. So that was telling us that the dominant leg was 64.5 seconds longer than the non-dominant. So that's how much we found was happening. And what would the randomization test is doing is saying, how likely is it to get a result of 64.5 seconds just by random chance? And so if we what they do is they take each of the data values and mix them up, randomly allocate them to the group and say, well, just randomly by chance, how often could we get this difference? And here we get a probability of 0%. So the chance of getting a result like this just randomly is 0%. So that tells me that actually you wouldn't get a result like this just by random chance. There must be something else deeper going on. And so the cutoff that we look for is 10%. So if our probability is 10% or lower, then that tells me I can conclude, I can make the call that doing this causes that to happen. And so that's what we can say here is the chance that random allocation gives 1.5 seconds or more is 0%. Okay, so that's just a little note for you. In terms of what I would want to write for the answer, I would just say as the probability is less than the cutoff of 10%, we can conclude that this result is unlikely to occur by random chance. And that means, so this means that, am I going to word this? If I go back to what I talked about at the beginning, we were looking at that cause and effect issue. We were talking about, does standing on our dominant or non-dominant leg cause a difference in the amount of time you can stand for? And what we're saying that we've got strong evidence that this is possible. We've got strong evidence for the people that we have experimented on. I can say standing on their dominant leg causes them to stand for a longer period of time. So that's what my result would be, is is that for these students standing on their dominant leg causes them to stand for a longer time than. Okay, so what we're looking for when we get this randomization test is we're looking at that probability to see how much evidence have we got just by random chance alone could we get it. And in this case, it's 0%, so that means it's virtually impossible to get a result like this just randomly. And so that means there really is something going on. And that's when I go back to thinking, well, what is it that we're comparing? And we're comparing standing on dominant and non-dominant leg and the time. So that's what we're analysing. Okay, you girls happy with that?
Yeah.
Awesome. Okay, so randomization distribution. So the distribution itself, and if I go back to the idea of experiments, the key idea is this random allocation, that we've randomly allocated participants into the two groups, into our control group versus our treatment group. And because this is the heart of what it is, this is what the randomization test is based on, is it's randomly reallocating people. So it's randomly reallocating the result into a different group. So in terms of the data, if I think about each of these points, then one randomization would take, for example, this particular person down here who happened to stand on their dominant leg for about 220 seconds, and it will randomly, it'll flip a coin and decide, is that now going to go into the dominant or non-dominant group? And so then it will randomly allocate that one to a group, and then it'll take the next point at about 200 and again flip a coin, randomly decide which group it is going to go into. And once it's done that with all of the points, it then calculates the difference in the median, and that difference in the median is one of the points that becomes on this graph here. Okay, so the key idea behind it is that it reallocates the treatment control group to each data point, calculates the difference in the medians. So what it's doing is it's saying, just by chance, what kind of result could you get? What difference in the medians could you get just randomly tossing a coin and putting things into groups? What results would you get just by random chance? And so that's when we can see these are the kinds of results that you'd get by randomly allocating them. And this is the one we actually got. So we can see that random chance is quite different from what our experiment result showed. So that's about as much as you need to know, as it's just doing a random allocation, because that's the core of what an experiment is. So that is experimental study designs. That's what we need to be able to do, is we need to be able to also think about, in fact, thinking about that one, we'd also have to think about what would we control. So if we're talking about standing on one leg, your dominant and your non-dominant, I've got a group of students in the room, what would some of the things I need to control be?
The surface they're standing on.
Good.
Make sure it's even.
Good. And so then we need to think more specifically, how would the different surface affect, and there are response variables, so it's how would it affect the time? So if we were standing on a carpet versus standing on a concrete floor, which of those surfaces would have more grip?
It'd be less balanced on the carpet, so time would be less.
Good. So that's what we want to be able to say as we're identifying we need to control the surface, because if you were standing on carpet, that would mean the time would be more or less. So we've been quite specific about that connection between them. Good. Any other ideas, girls?
Shoes.
Good. And so how would shoes affect your time?
Well, if you're wearing heels, you'll probably fall faster.
Good. Perfect. That's exactly what I want you to be able to tell me. Anything else?
Guess if you're outside, there might be wind.
Absolutely.
Very
Absolutely.
well.
Gusts of wind. Yep. And if you're standing in a classroom, is it okay if you're standing shoulder to shoulder with someone?
Oh, they'll bump you and you'll
Yeah.
both fall.
Absolutely. So having space around you, enough space that you're not going to put knock people over or put people off. Good. So those are all things that we would need to control, because the more we control it, that means that the experiment is only testing the thing that we really want to know, so that these results that we get are quite going to be much more significant because we've controlled everything. Cool. All right. So that's our experimental study design stuff. Then we have some stuff about, lots of stuff about observational studies. So most data that we get is observational. And what we want to do is think about, first of all, how was the data sampled? So we can have either random or biased methods. Now, random methods are good. We like random methods. And the key word there is the data is going to be representative. And I love the formatting changes everything. Sorry, it's a pain. So what we want to do is we want to use that word representative when we talk about sampling method. And these are the 4 methods that give us our random ones. So do you know what simple random is? Okay, so simple random is literally kind of like names in a hat. Yep. So when if I was to put our names in a hat and pull them out one by one, then that's just a simple random sample. Stratified. Stratified is when I have multiple groups, so or strata. So I might separate the groups first into males and females, and then take a sample within the females and a sample within the males. Or like they are doing a bit more with like the COVID testing stuff at the moment, they're talking about different ethnicities and what percentage of ethnic groups have been got their vaccinations and stuff. And so that's an idea with if you separate it into ethnic groups and then sample within each of those groups, then that will be a stratified sample. Systematic. Systematic is if I have a list of people's names, I am going to systematically choose. So I might start with choosing the 3rd person on the list, and then I'm going to choose every 4th person on the list after that. So there's a system behind how I choose them. And cluster sampling. Cluster this is to do with geography. So if I think about if I was going to sample at our school grounds, we know that, for example, we've got our Goodfellow quad and our Elliott quad, and we've got the fields and so on. And I might just randomly choose to go and sample a bunch of people on the field. And that would be a cluster sample. So I've separated it into geographical locations and then sample within that. And I'd need to randomly choose which area to do, but then that makes it into a random sample. So those methods are all good because they are random and they will give us data that is representative. So we like those. Bias methods. Bias methods gives us ones that are over or underrepresented. So for example, if I did a convenience sample, so I stood at the local supermarket and I just sampled people that walked past, That's convenience, and it's only going to be sampling people that happen to be in that location at that particular time. So if I was doing it during the week, middle of the morning, then groups that would be overrepresented might be young parents, young mums who are home with kids, or elderly people who are retired. So those would be groups that are overrepresented. What groups would then be underrepresented in that situation?
People who aren't in the area.
Good. So anyone that doesn't live in that area or work in that area won't be represented. What else? So apart from, think about who's in our population, apart from, say, younger mums and retired people, who else would live in any area? What other groups would there be?
Working adults.
Good, good. So all adults that are at work would be underrepresented. Who else? What about students?
I was just about to say that.
So students would be a group that will be underrepresented, both school students and tertiary students. Yep. So yeah, so that's what you want to be able to talk about with bias, is that you want to identify
Ooh.
a particular group that's underrepresented or overrepresented.
I have one.
Yeah.
Disabled people that can't do their own shopping.
Oh, nice. Nice. Absolutely. Cool. And so then the other bias method is our self-selected method there. And self-selected just means they're volunteers. So think about people who volunteer to get blood tests, also to get to give blood. They are different. They have to be certain weight, height, age, health status, etc., etc. So they are different. People who volunteer are different in some way. And so you'll have an overrepresentativeness of some people and underrepresented of other people. So those are our sampling methods. Then we have our survey methods. So this is looking at how do we actually collect your data. So samplings, how do we choose people? Survey methods, how do we collect the data? And we want to look at advantages and disadvantages of those methods. Sampling error, we always have sampling error present. That's always there as soon as we take a sample. And non-sampling error, those are the things that we have some control over. I can't control sampling error. It is simply present. As soon as I take a sample, I have it. Non-sampling error, as the person designing the sample and survey, I can control this to a large extent. So I can, for example, look at response error. So that response error is about people giving me truthful answers. So when I write my questions and my choice of surveys, I can try to choose methods that are going to get me the most truthful answers. So if it's a sensitive topic, I might want to do more face-to-face interviews. People are going to be more truthful face-to-face. If it was something to do with, for example, STDs, by choosing to have a doctor do the survey, they are more likely to get more truthful answers out of participants. So the choices that I make can limit my non-sampling errors. Non-response, that's about people who, the people who don't respond can have different opinions and different data than those who do respond. So if, for example, I've asked a bunch of people, would you like to participate in my survey? And there's been some people that have said no. Those people that have said no, they will have different opinions and data. Cool. Okay. Selection error, that's talking about, again, the idea of some groups being over or underrepresented. So even if we do a random sample, it is still possible to get a bit of that happening. So by choosing to do a random sample but only using people's on phone, I know some of the groups that are underrepresented there will be homeless people, people without a phone, and so on. So selection error is about which groups are overall underrepresented because of the choice that we made with the survey method. Self-selection, so that's our volunteers are different, they'll give different answers. And the survey errors, that's looking at the wording of the questions, the order of the questions, anything to do with the actual survey itself, and the errors that come from that. Okay, so then we talked also about, so that's about critiquing a survey, and they will always give you a bit of a report and ask you to critique it. And they might be explicit with their questions and say, what are some of the non-sampling errors? And sometimes they might just give a more general question, say, critique the survey. And you just want to do a bit of an evaluation on that. So that also leads to the overall evaluation. Response rate, how good was your response rate? 10%, 80%. Those are quite big differences. The higher the response rate, more data, better we've got it. Whereas things like sample size, now this is where you are just going to add a little note of caution. Sample size is important, but there's a point of decreasing return, if you like. And one thing I don't want you to think about with sample sizes, I don't care how big my population is. I only care how big my sample is. So I don't care that I'm sampling from 5 million people in New Zealand and I've got a sample size of 1,000. That 5 million is irrelevant. Okay, the only thing I'm interested in is the fact that I've got a sample size of 1,000 people and how much data is that 1,000. And that 1,000 people is quite a bit of data. So therefore, that's what I'm interested in. Okay, the population size, we don't really even consider that to be an issue. And if I think about my margin of error, when we do those margins of error, and we have, I'll just flip to the next page, when we have that formula for margin of error here of 1 over the square root of n, we only take into account that sample size. It's the only thing that gives us an indication of how accurate our results will be. So yeah, so there we go. In terms of confidence intervals, I'll have a quick look at that in a second about whether we can make the claim or not. And in terms of our conclusions, because we're doing observational studies, we always want to use that inferential or suggestive language. Sometimes we talk about correlations, and so that's kind of some of the things that we want to make sure we talk about. In previous years' exams, they occasionally have talked about, like once every 4 or 5 years, they talk about this idea of lurking or confounding variables. And what that refers to is if I have some data on how much activity people do, and I have some information about their risk of heart disease. So those are 2 variables I have. The lurking or confounding variable is saying, is there another variable, which in this case would be age, that connects to both of those variables to explain the relationship that I might see? So if I was to draw a graph of activity levels versus the risk of heart disease, I would expect to see as people with higher activity levels I would expect to have lower risk of heart disease, and people with high activity levels would have a high risk of heart disease. So that's the kind of relationship I would expect to see if I collected data. But what we do know is behind the scenes, it's actually this variable of age that is contributing to both of those things. As people get older, their activity levels go down. As people get older, their risk of heart disease goes up. So the age is our lurking or confounding variable. It's the one that's behind the scenes. And this is because we're doing observational studies, we're not controlling all of the variation. And so that's where we get these lurking and confounding variables, because we haven't controlled all of the variation that we have. So the difference between them, they both of this refer to this variable behind. One of them, though, is when you've in a set of data, did you collect data on this variable or did you not? So a lurking variable, that is when I have, get this the right way around. The lurking variable is when you have collected data, or collected this variable. So you've got information on that specific variable, but you're not drawing it on that particular graph. Whereas the confounding variable is when you did not collect that variable. So you haven't got any data on it, but that's when you're just talking about what else could be behind it. Okay, so as I said, that comes up every, once every 4 or 5 years, that comes up, and they'll just ask you in a situation, what is a possible confounding or lurking variable? And you've just got to think, well, what else is connected to both the variables that I can see on that graph that could explain some of that relationship behind it? Alrighty, so that's about collecting data and so on. And this is a little reminder about our confidence intervals. So 3 types of scenarios. I have my no comparison. So this might be, for example, I just want to know what percentage of people voted for Labor. And I just want to know, well, in the latest survey, it said that it was 45%. Well, let's make a confidence interval with that. And so I might get a confidence interval that comes out as 45% plus or minus the margin of error of, say, 3%. So that means my confidence interval goes from 42% up to 48%. Now that confidence interval, remember we're doing observational data, so it's sample to population. So what this is doing is this is saying in my population, the percentage who would possibly vote for Labor could be anywhere between 42% and 48%. So our confidence intervals, any time of confidence intervals, are estimating the population from a sample. Okay, so that's what that confidence interval is it's estimating what the population might be based on a sample. So no comparison, we just use our margin of error formula 1 over the square root of n. Then we get to our comparison within one survey. So that might be if I want to compare the percentage who voted for Labor with the percentage who voted for National. And so I'm comparing these two. My margin of error now has ×2. So it's within one survey. I've got one sample size, but now because I'm doing a comparison, the margin of error doubles. And when I come to calculate my difference, there might have been a difference, say, of 5%, that Labor was 5% higher than National, plus or minus, let's say, 6%. And that would give me a confidence interval of -1% up to 11%. So when we get to these confidence intervals, when we're comparing, a little reminder that we are looking whether is 0 inside the confidence interval. Okay, when I say both limits are positive, we're saying is 0 inside. In this case, 0 is inside. So can I say that there is a difference? No, I can't. If 0 is inside, they could be the same in the population. Okay, in my sample, there's a difference, but in the population, there might not be a difference. So that's what we want to be able to do there, is we want to compare inside a single survey and look and see, is 0 inside that confidence interval? Then the third type, comparison between two surveys. So I might want to compare the percentage that voted for Labor in 2020 with the percentage that voted for Labor in 2021. So I'm comparing two different surveys. The first one might have had a sample size of 1,020, and the other one might have had a sample size of 1,300. So I've got two different sample sizes because we sampled different people. So in that case, we do our margin of error for each sample size, do the average times 1.5. But we'll still get a confidence interval. And so say I got a confidence interval here where say that it was, let me just say 3% and 8%. I could look at that and say, is 0 inside that confidence interval? No, it's not. So because 0 is not inside, I can say, look, the amount of support for Labor has increased by between 3 and 8% over this time period. So this is talking about the difference, okay? And it's telling me which one is bigger or smaller. All right, are you guys all happy with that?
Yes.
Okay.
Yes.
All right. So I've got some more, if you do need more particular practice on this, and this is an area, the scholarship examiner changed a year or two ago. And so the style of questions in the last year or two are slightly different from the previous examiner. And the reason that this is important here is the previous examiner did not really do margins of error confidence intervals at all. But if you look at the last year or two of scholarship exams, they have actually got questions in the exams about margins of error and confidence intervals. So this is why I'm just saying this will be an area that a lot of people traditionally may not have done any work on. But if you've done a bit of prep on this area, that will definitely help for this year. Okay. So then we need to be able to analyze our data. And so this is when we've got observational data, there are the 4 different types of inference. And so this will be the stuff you're a bit more familiar with. We already talked about our experiments and how we analyze those. But then we've also got our comparison, doing an inference, looking for relationships, having a bivariate, and then our time series. So we've got our different features, shape center spread for experiments and comparisons. That's those same features. Then with our bivariate, we want to talk about trend, direction, strength, outliers, variations, and I'm going to talk a little bit about clusters a second as well. With time series, we also have that same trend, and we have the same variation and outliers, but then we also have that seasonality that we talk about with the time series. So let's go and have a look at a couple of examples of those and jog our memories about them. So let me jump into here. Oh, and I'll come back to that paired experiment. Okay, so great spotted kiwis. I've got great spotted kiwis and I've got North Island brown. First thing I want to do is analyze my features. So shape there, what would you guys say about the shapes of those?
Normal?
Yep. I'd be happy to say they're roughly normal. They're not perfect, but roughly normal. It's a sample, so they're pretty good. Then center, what would we compare for center? Let's go for medians. Yeah. So we want to compare the medians, and we're talking about the median weight of our great spotted being 2.884 kg, and the median weight of our North Island brown being 2.486. Which one is slightly heavier?
Great spotted.
Yep, absolutely. And we'll find that difference between them. So in terms of my shape, I just want a very quick note there. The shape of the weights of both great spotted and North Island brown kiwis is normal. And for my centre, I'm going to say the median weight of great spotted is, and that's going to be about 400 grams. Let me just go to 2.84 minus 2.486, 0.398. Okay, so nearly 400 grams. 398 kg heavier in North Island brown. Okay, and spread. If I want to compare, and I could actually quite happily compare my standard deviations for these ones, or I could compare the interquartile range because it's roughly normal. So I could actually do both, and even with the mean compared to the median, we could accept both of those, mean or median, because it's normally distributed. So which one is more spread out, Great Spotted or North Island Brown?
Great spotted.
Awesome. That's all I want to say there. Spread of Great Spotted is larger than North Island brown, and that's when I would write down my standard deviation equals or awesome. So there's shape centre spread, very quick analysis of the features. Okay. So then we want to think about our conclusion. So now when we do our conclusion, this is when we have our bootstrap distribution. So let's have a look at our graph here. Now the graph at the top is just the same dot plot box and whisker graph that we had before. So it's the second part, which is the bootstrap part. So this is our bootstrap. And what we notice is it's got on that arrow there, it's got that value of 0.398. So that is the difference in the medians. And that was when our Great Spotted is larger by 0.398 kg. So that's where that number comes from. So that difference is the difference in our sample. What our confidence interval is doing, that is estimating for the population and saying, well, what could be the difference? How much bigger could the Great Spotted Kiwi be? And it could be between 0.153 kilos and 0.5095 kilos larger. So that's what we want to first of all say, is to say what that confidence interval is. So 8 for the population of kiwi birds, that the Great Spotted kiwis are between 0.153 kg and 0.5095 heavier than the North Island browns. Okay, So that's what the confidence interval does, is estimates for the population. The population median is somewhere in this range. And now I need to decide, can I make the call? So do you remember what we look for in that confidence interval to decide if we can make the call?
Overlap.
Yep, and overlapping explicitly with 0. So what I want us to look for is, does the confidence interval include 0? So that's that same idea that we looked at with the confidence intervals for with margin of error. So let me find that page. That one. Here, when I talked about there is 0 inside that confidence interval, we want to see exactly the same thing happening here. Is 0 inside that confidence interval? Can I make the call? So for this one, does this confidence interval include 0?
No.
Absolutely. So 0 is there. The first value starts at 0.153, which is above 0. So it does not include 0. So that means as 0 is not inside the confidence interval, we can make the call that the great spotted kiwis, I should use the word median, that the median weight of great spotted kiwis tends to be heavier than the North Island brown. So again, I'm wanting to refer to the population, and so I should actually be good and say for all kiwis, and to include that as my population of all kiwis. Okay, so features, shape, centre spread, conclusion, interpret the confidence interval itself, and then can we make the call depending on whether 0 is inside that interval. All right, are we happy with all that?
Yes.
Okay. So who remembers much about the bootstrap distribution? Yes, there's some of us that did this earlier this year that we should remember hopefully a little bit about it. And I remember I made you write some stuff down about bootstrap for one of the scholarship classes at the beginning of the year. Let me just see if I can find, there was a poster that, oh, this one, yeah, there we go. So this is the bootstrap distribution idea. There we go. So the key idea is we take a sample from our population and we take as much sample size as we can afford with the time and money we have available. So we take our biggest sample that we can get. But now what we want to do is use that data more effectively. And so what we do, or what we make the computer go and do, is it goes away and resamples 1,000 times. So it creates 1,000 new samples from our sample. And then it calculates the difference between the medians for each of those and plots that bootstrap distribution graph. So that bootstrap distribution graph, that's the one we've just had a look at here. So this is that bootstrap distribution graph. There are 1,000 dots on this graph, and each dot on that graph is when they've gone away and resampled from all of the data there and calculated the difference in that median, plotted that, then taken a new sample. And so it goes off and resamples that. So that is what our bootstrap distribution is. So just a quick little reminder there. We'll just paste that. That is what bootstrap is. Do we kind of remember that now?
Sort of.
Okay, I'm going to say don't stress too much about it. I know if I go back 8-10 years ago and look back at some of those previous exam papers, that was when the bootstrap was first introduced. And so in those older scholarship exam papers, they actually had questions which said explain this bootstrap distribution. And so that was asked then because students didn't know what it was. The current examiner is more focused on, yes, we want to have an understanding of it, but it's more about being able to interpret those results. So being able to look at the graphs that we get, those bootstrap graphs, and being able to interpret those confidence intervals, draw a conclusion, can you make the call? So that's what the current examiner is focused more on, because in the past they have asked questions already about how the bootstrap distribution works. So yes, it's important to know and have an understanding behind it. I'm going to say probably don't stress too much about remembering this one though off by heart. Okay. All right. So that's our inference. Let's have a look at bivariate. So this is when we're looking for a relationship. So here what I've got is I've got kiwi birds again, and I'm looking at the heights and weights, and this is all of my kiwi birds. So features for a bivariate graph. What are the features that we want to talk about? So we want to do these ones: trend, direction, strength, outliers, variation, and I want to go on to have a quick look at that cluster part in a minute. So let's start with trend and direction. So trend. Does it look like I could fit a straight line through that data, or does it look more like a curved data set?
It looks like a splatter, to be honest.
And this one is harder to see. And so sometimes what I'm looking for is where the data is, but also where is there not data. And what I do notice is that there is no data up there and there is no data down here. So if this was just a completely random graph and there was no relationship, I would expect data everywhere around here scattered. But because I've got these two small sections where there is no data, that means I can't have no relationship. So there is a relationship, but it's going to be very weak. Yeah. So given that that kind of is where the pattern of data is going, would you fit a straight line or a curve to that?
Probably a straight line.
Yeah. The rule of thumb is if you can do a straight line, that's the easiest to use and the easiest to explain to anybody that needs to model this data. So if we can do straight line, we use straight line. It's only if it looks really non-straight line that we have to use other models. So we're going to go with this being a linear model. Okay, what about the direction? Is it increasing or decreasing?
Increasing.
Good. So we've got a linear model, an increasing relationship, strong model to weak.
Weak.
Quite weak. There's a lot of scatter going on there. Yeah. And what about the variation? Now, do you remember with variation we talked about variation could be constant, or we could have our fan or funnel effects? Yeah. Do we have any fan or funnel effects here, or is it pretty constant variation?
Pretty constant.
It's pretty constant. And the reason I can say it's pretty constant is if I look how wide it is here and how wide it is here, at any point, there's a slight difference between it, but they're mostly about the same kind of level of variation. So it's pretty constant variation going on. Okay, so that's what we want to write up and explain. So, oh, I need to identify my variables actually. Explanatory, response. Explanatory is our x-axis, and response is always the y-axis. So in this case, our explanatory will be the weight of the kiwis, and our response will be the, sorry, wrong way around, height of the kiwis, and our response is the weight of the kiwis. So it's just a matter of going x versus y, and that's always your response and explanatory. Okay, so analyze our features. So I'm going to say there is a linear, if I can spell, linear, positive, weak relationship between the height and weight of kiwis with constant. So one sentence, and I just throw everything into that one sentence, all of those features. Linear, increasing, weak, constant, just throw them all into a sentence and make sure it's in context. So it says that it's between the height and weight of kiwis. Here's my context. And then for justifying, when we justify, we always want to talk about as the x variable increases, the y variable, and that either increases or decreases. So in this case, our x variable is height. So we would say as the height increases, the weight is increasing. It's a very weak relationship, but there is still a relationship. So we would say there, as the height increases, the weight increases. We can talk about there is a lot of scatter. And of best fit. So those are the two things that we would do. Let's talk about as x increases, y increases, and there's a lot of scatter because that's why we're going to get a weak relationship. So that's our overall analysis of the sample. When I look at that graph, we want to see, are there any outliers? So when I look at this, now that I've scribbled all over it, an outlier has to be something that's a long way away from that pattern or trend. So we've got that pattern as that main strip in the middle, okay? That pattern there, so an outlier would have to be a point, for example, that is over there, okay? Way away from the pattern itself. Anything that if I look at there, the data there, there's no obvious outliers that jump out at me. They're all just variation within the pattern that we see. But when I'll just look at this graph for a second. When I look at the data here, what you can faintly kind of notice is that there is like a blob of data here and another blob of data here. And so I start thinking about, have we got clusters? And when I actually go off and I talk about, if I here now colour it in, I've coloured it in by the red dots are my great spotted kiwis. The green and the blue dots, they're my other two species, the North Island brown and the Southern Tokieka. So when I actually colour these in, now I can actually see there are definitely these two clusters that are within our data set. So it's not always easy to see that from the original graph. Okay, if I take those out, it's harder to see that, and that's why we use the colouring in technique to actually look to see and explore for it. So we can sometimes have clusters, but when we talk about them, we need to be quite careful to identify it, because unless we know a bit more about why there might be clusters, it's better to not say anything at all. Because particularly my year 11s are terrible at telling me where there's clusters when there actually aren't. They just like to use that word all the time. So if I have clusters, like if I look at this one here and I look at this model that's been fitted, so if we look at that lovely straight line that we've got through the middle, how good is that model? How accurately is that going to make any predictions for us? How much variation is there in the data?
Lots.
So if I've got a lot of variation going on in my data, how precise and reliable are my predictions going to be?
Not very reliable.
Absolutely. So when we talk about the fit of the model, let's talk about that fit of that straight line there. We really want to think about that strength. Okay, so the strength is really important when we talk about it. And in this case, because the strength is weak, there's a lot of variation. So our model doesn't actually fit that well. Whereas if I had a graph that I collected some data and that's what it looked like, I could fit a really good model to that one. I could fit a straight line to that, come up with the equation of that, and that would be a really awesome fit because the data is very much together, concise, and therefore will give us much more accurate estimates. So for this particular model here, we would say the model does not fit very well because there's so much scatter and variation in the data. Okay, so that's what we want to do when we talk about the model, is how well does it fit? And in this case, it's not a great fit. But if I take that idea of fit, how well it fits, one step further, when I now break this into clusters, if I actually now know for sure we've got these clusters going on, how should I actually analyze this data? Should I have them all together or should I be separating them? My argument would be, because I've got these two groups here, what I really want to do is I want to just pull out those great spotted kiwis. And I want to draw a separate graph just with those great spotted kiwis. Then with these ones here, again, I want to separate those out and make a graph either of them separately, or I could put them together in one graph. I could argue for both. But that would be what I want to do, is because I know I've got these clusters, actually I want to separate that data out and analyze each cluster separately, because there could be quite a different relationship between them. And so that's what this very last graph here has done. So what I've done here is I've separated into, this first one is my great spotted, the next one is my North Island brown, and the last one is the Southern Tokieka. And so we've separated them out because we've seen evidence that they are actually separate clusters. And then when we fit the model, so when they fit the line of best fit to each of those separately, hopefully we can start to see that actually the model fits a little bit better now than it did when it was all together. So when it was all together, that is really a terrible fit. But by separating them out, it's a much better fit. And so how we can measure that is this statistic here, this R value. Now, I don't know if you guys have come across the R value before. I can't remember if I talked about that earlier in the year or not. Did I talk about the correlation coefficient? Can't remember. So correlation coefficient is just a way to measure how good that relationship is. And we can see these ones, it's 57, 52, 53. So that's about 52, 53, 57%. So it's saying 57% of the variation can be explained by this one variable. Whereas the correlation coefficient here was only at 50%. So by splitting it out, we've improved that slightly. The fit of the model has improved slightly. It's still quite a bit of variation, but it is a little better than it was before. Okay, so that's kind of the idea behind that. So what did I say in this one? What does that suggest? Because we have clusters, we should analyze each cluster. And when we do that, that improves the fit of the model. And we can see there that the equations that we would get, they are all got slightly different. It's the thing about how steep those lines are, the gradient of those lines is different depending on which species they're talking about. So I would say that the models fit better. See the correlation coefficient. But are still containing a lot of variation. So it's still variable, but better than it was. Okay, so there's bivariate. Time series. Still want to talk about the trend. We also now want to talk about seasonality, and we also want to talk about the variation and outliers. So, time series is our trend line going through the middle. Is it increasing or decreasing?
Increasing.
Good. I've got an increasing trend. And notice that I want to, now when I talk about that trend, I want to use those average values. I don't want to use the individual data points from the graph, okay? Because the trend is that overall pattern. And so I can talk about an increasing trend between 2000 Q1, and that's from around 139,000 people to 2020, is it 2000? No, it's just this last point here finishes, you can see the grid lines, it doesn't get to 2020, so that's actually 2019 Q4. So I'm going to delete that. It's 2019 Q4. The average number of visitors got up to 383,000. So these are visitors coming from Australia. So over the last 20 years, the number of visitors coming over from Australia has increased quite a lot, 139,000 up to 383,000. Okay, so that's our overall trend, what we want to say about that. So that's our first part, is trend is increasing from an average of 139,000 visitors in 2000 Q1 up to around 383,000 2019 Q4. Okay, so that's our trend. What other features do we want to talk about?
Patterns or seasonality.
Good. And so when I look at this graph, it looks like there, if I look at that day-to-day, that quarter to quarter pattern going up, down, like this, it looks like there is a repeating pattern going on there. And to see that better, we are going to jump down to our seasonality graph, which I've got there. So this is what the seasonality graph has just taken each year, that pattern each year, and copied and pasted it for each year. So looking at this graph on the left, if I look at each year, they all start by going downwards. Then they all go upwards. So is there a consistent seasonality pattern?
Yes.
So that's the first comment we're going to make. There is a consistent seasonality pattern each year. Yep. Notice whether or not we have one. Then we look at this graph on the right. And so that graph there, this is our summary. Okay, so what it does is it takes each of the first quarter points, compares them to the trends for each year, and then finds the average of all of those. And so that's what this first point there, that's the average of all the first quarters. So the line at 0, that is our trend line. Quarter 1 then, so that's our quarter 1, that is above the trend line. Quarter 2, below the trend line. Quarter 3, just below the trend line. Quarter 4, above the trend line. So we can see there that's the overall pattern, that it tends to be highest in which quarter?
4.
And lowest?
2.
Good. So that's what I want to now do, is talk about that peak and that trough. So I first of all say, is there a consistent pattern? And then I want to say it's highest here, lowest here. So I'm going to say the peak is in quarter 4, and then I want to say how much that is. So estimating that quarter 4, I'm just going to delete that bit off. And if I had to kind of estimate how much that would be going across here in a lovely straight line, let's go with around 40,000 visitors more in quarter 4. And quarter 2, let's go around 45,000 visitors less in quarter 2. So we only need to estimate them off the graph. We don't need to stress if it's not 100% accurate. So peak is in quarter 4 at around 40,000 more visitors than end, and trough is in quarter 2 at around 45,000 less visitors. So that's what I want to do, to say highest and lowest and estimate the number that it's in. Okay, so that's our seasonality pattern. Seasonality and trend. What's another pattern that we look for? So when we do that, we've done our trend, we've done our seasonality. Another one is that variation, looking at whether the variation is constant or whether we have that fan funnel effect going on. So if I am going to jump back up to this first graph here, what I'm actually going to just do is I want to just take that off for a moment. And I am going to draw a line hitting the top peaks here and a line roughly hitting those bottom troughs. So when I draw that, what can you tell me about the variation? Is it increasing? Is it a fan effect, a funnel effect, or is it pretty constant?
A slight fan.
Yep, absolutely. That is getting wider. It's not huge, it's not quickly getting wider, but it is definitely getting wider from the start to the end. So we can also talk about that variation. So I could say there is an increasing variation in the number of visitors arriving over this. Yep. So that variation is increasing over the time period. That's the key idea. Okay. So trend, seasonality, variation, and the last one we can do a double check with is our outliers. So to check on outliers, we want to look at our recomposition graph. And so that's when I've got this next one here. So this is our recomposition graph. And in particular, I want to look down at this residual part down the bottom. And what I want to do is I've got these two little grey lines. And those little grey lines are the boundaries. That talks about how much variation would be normal. Okay, so this is like our upper limit and our lower limit. They're just essentially confidence limits. And about 10% variation is normal. Okay, so 10% variation is normal, and that's how they calculate it. And so what we want to do is identify, are there any points that have gone outside this normal amount of variation? And when I look at that data there, so when I follow the data, it all looks like it is staying within those limits. There's nothing that's gone outside of the limits. So, do I have any outliers?
No.
No, I certainly don't. So that's what I'm just going to say there. So the first thing I'm going to say, there are no outliers as the residuals are all within the limits. Okay, but the other part of this, identify the type of model that should be fitted to the data. And this is where what we just looked at with the variation, that's where that becomes important. So if we have an increasing variation, as soon as I have that fan or funnel effect going on, then what our normal is, and this is why we have this recomposition graph, is it normally splits it into a trend plus a seasonal model. So this is what we call our additive model. Come on, switch pens. Additive. It does a trend plus a seasonal and combines them together in that additive way. If the variation is constant, then an additive model is good. However, if we have a change in the variation, then a multiplicative model is better. So because we have a fan effect, okay, because we have a fan effect, a multiplicative is preferred. Okay, and so that just means that instead of that model being trend plus seasonal, we should be doing a model which is trend times seasonal. That the model that will better take into account that change in the variation over time. So that's the key, is if the variation is constant, we use our additive model. If it's not constant, we use a multiplicative model. Okay. So what we then want to do, if I skip past that, is this is now the having actually fitted. So this is just now fitted the additive model. So this is fitted the additive model. And what we want to look at is how well does that model fit? Does it fit really well? Does it not? So your so the green line, this historic predictions, this is your model. Okay, the black line, that's your actual data itself. So when I'm looking at this down here, what I'm doing is I'm trying to see how well does it fit. And if I have a model, so say I had my data doing this and my model doing almost the same, then that would be a really good fit of the model. The actual data and the model are almost on top of each other. So that would be a fantastic fit. If I had that and then my model did this, then that would be a terrible fit because the model doesn't follow the same pattern as the data does. So what we want to look at there is how well does that model fit for this one. So if you think about, 0% to 100%, 0 being it's horrific, 100% being absolutely perfect, which you never get when you're doing data, where would you girls put this? Would you say this is, 80% of the way there, 60% of the way there, 20% of the way there? How good a fit would you say this is?
I think it's pretty good.
Good. And why do you say it's pretty good?
It follows it quite closely.
Good. And so that is the reasoning I want you to be able to give me. So what we want to be able to say is the model fits quite well because it tracks data most of the way. Something about that, something about it following, okay? So something about the model following the patterns, basically. That's what we're looking for. Can you identify any areas that don't fit very well? Could you give me an example of a place where it doesn't fit very well?
2002.
Okay.
4.
Yep. So I can look particularly here, here, here. So I can identify particular points where the model doesn't fit as well. And so that would be a really nice thing to add in your explanation so that it tells us that you know what it is that we're looking for to identify if it's a good or bad fit. So that's when I might say, for example, and let's go, that would be in 2002, the model doesn't as well, but 2000, it fits much better. Okay, so just identifying a couple of particular points so I can see the example of here's a good fit, here's not a good fit. Or if you're drawing on your diagram like that, you can just circle it and just put little notes, fits well or doesn't fit well. That's another, you can just put notations on the diagrams as well. That would be quite cool. Okay, so now I want to dig into that a little bit more. What was the trend doing? So we go back to that trend. The trend, we said that the trend was increasing. If I look at that trend line, does it look like a roughly, almost a pretty steady increase, or is it quite jerky? So if I was talking about, what I'm thinking about is if I had a trend line that went like this in a piecewise function, that means the trend has changed quite significantly. So there was a period of time where it increased really steeply, then the trend actually turned around, and then it increased again. So that was quite a significant change. If we look at this trend line here, would you say there have been any significant changes, or has it been roughly consistent?
Roughly consistent.
Yep. So that trend is going up reasonably steadily. It's not perfect, it never will be. We've got data, but it's going up. It's certainly not changing direction at any point in time. And because of that, the model will fit better. So when they try to fit that model, because remember they're doing trend plus seasonality, they're adding them together. And if we've got a nice steady straight line pattern to do, that's what they're doing there, is they put a straight line through the middle of it. And they said, because it's a roughly straight line, that means our model's going to fit better. Also, when we look at our seasonality was pretty consistent too, wasn't it? And we can see that from the graph, the model turns up and down at the right times. That pattern is doing it right. There's times when it might not go quite as high or quite as low, but it goes up and down at the right times because we've got a good seasonality in there. And so those are the things that help the model fit better. So I can add a little note there that says, because the trend is roughly steady and the seasonality is quite consistent, the model fits. So if you didn't have a nice seasonal pattern, the model wouldn't fit as well. If your trend changes direction, those are going to be where the model doesn't fit as well. So those are kind of things that are going to all contribute to how well the model fits. Just like with the bivariate, that clustering affects how well the model fits. Okay, so that is, what am I doing? Come back to this one. So that's looking at being able to analyze and draw conclusions for our different data. Okay, so all of that so far, that is about 80% of your exam. 4 of the 5 questions are going to be about all of this stuff. All right, so knowing what to do with experiments and analyzing those graphs, being able to critique a observational study, being able to do some confidence intervals, and then analysing and drawing conclusions for our data. There's 80% of the exam. The other part is on probability. So what I've done with the probability is I've pulled through some of the images and stuff that I've made to try and help understand these big ideas. Now, some of these you guys will have already gone through and done, and others of it will be newish. So, because I know depending on whether you're doing IB or NCA or level 12, year 12 or year 13, depends on where your particular knowledge is at. We'll start with the fact that we've got several types of probabilities: theoretical, experimental, and simulation. So the theoretical, we know that's almost like the true probability. Okay, so when I toss a coin, I know that there's a 50% chance. Unless it's a weighted coin and they've screwed it up, there should be a 50-50 chance of getting a head or a tail. So that's the theoretical probability. However, if I now go and toss that coin 20 times, I'm not always going to get exactly half of those as a head. And so that now becomes our experimental probability. We're not actually experimenting and collecting data. And so we can experiment with things that we know the theoretical probability for. Usually, though, we experiment with things we don't know. How likely is it that we're going to have a connection issue on the call? And that's something I can only do by collecting data. I can know I don't know the theoretical probability of what the chance of having a connection issue is. But if I collect data over a period of time, I can say, well, 5 days out of 7, the connection's really good. And that now becomes my experimental probability, which is trying to predict that true probability. Simulation. Simulation is when you build a model. And so they've been doing a lot of that with the COVID stuff, is they simulate, they approximate the situation and use a number of different tools to estimate what would happen as a result of. And so those are the three ways. So when we talk about probabilities, those are the three types that we can talk about. Now, a lot of, you don't do much with simulation. I don't think I've seen a simulation question in a very, very long time in scholarship. So being aware of it, but most of the probabilities they ask tend to be just about either experimental or theoretical probabilities. So there are, when you're trying to build any kind of model, so your experimental probabilities, there's three tools that we can use: tables, tree diagrams, Venn diagrams. Most of the time, they just give you the data and you get to choose which version you prefer. So if you don't know anything about Venn diagrams, I'm not going to stress about learning that at this point in time, because the questions only ever give you information and you choose how you display that information. My personal choice is using tables. I like tables. Tree diagrams can occasionally be quite useful, but that would be how I display data, is by preference. The idea of and it's reminding us, and if I see that word and, we are always multiplying. And says A and B, they both have to occur, and that's why you multiply, because the chances are small that both of those things occur. Or means I'm going to add. I could have A, or I could have B, or I could have both of them. So or means all of those. I'm going to combine them together. Either means I don't have the bit where I can be both. So if either I go to school or I wear a hat, I couldn't do both of them at the same time. So either can't have both. And that's why you can see in the diagram there, I don't have this little bit in the middle shaded in, because I can't have that overlap. Not just the opposite. So if I say the chance of a head is 50%, not getting a head, the opposite is 50% as a tail. Conditional probabilities. And so that is the idea of when you're given more information. I'm telling you that I have a male sitting in front of me. And now what is the chance from those males that they play football? So I'm going to look at the chance of football out of the total for the males. So that's the idea of conditional, is it's a combination divided by a particular group that you've split it into. And that's what the formula is. It looks more complicated, but all it's saying is do A and B, so do that combination divided by the total for group B. So you're always doing it by a subgroup. Expected value, E equals N times P, is a formula that I'm hoping some of you are familiar with. And so they can ask you what's to calculate the expected number of. Relative risk. Relative risk is a comparison. Did I put it down? No, I didn't put it down. So relative risk is always a conditional probability divided by a conditional probability. So I might want to compare the males with the females. Those are my two groups. And I might want to compare what's the chance of drinking alcohol if you're a male versus drinking alcohol if you are a female. And I would expect that there's more males that drink, so that risk might be, say, 3. And that means that men are 3 times more likely to drink alcohol than females. So it's that idea of relative risk. The word relative means compare. Compare this with that. So compare the risk of one thing with the risk of another. And it's used a lot with medical stuff, actually. It's, what's the risk of this compared to the general population? What's your risk of getting COVID if you're vaccinated compared to unvaccinated? That's what it's doing. It's doing a comparison between two groups. Then we have a few probability rules. Now, this is in the Level 3 concepts paper, so I know the NCEA kids won't have seen this. I don't know if you IB girls have seen these ones before. So these particular ones, have you come across those before, Michelle? Okay. So these ones are a way to, it's just putting into formula the idea of what these things mean. So the idea of mutually exclusive, it means events that cannot happen at the same time. You can either be hot or you're cold. You can either go north or you can go south. So it's talking about mutually exclusive, it's the opposites of one another. Okay, two things that can't happen at the same time. So it's just saying that the intersection, you can't do them both. That's what this little symbol there just means, is intersection. Okay, complementary. Complementary just means that they are the only two possible outcomes. So hot and cold are the only possible outcomes. Whereas if I take direction, I can go north, south, east, and west, so that they would not be complementary events. North and south, if I just had those, that would be complementary. So it just means the two things have always got to add up to a probability of 1. Now, the ones that have come up in questions before are these ones about independence. Okay, so the first thing I want you to think about is, what does it mean to be independent? If two events are independent, that means that doing one thing does not affect the chance of the other. So if I say my decision of what to eat for lunch is independent of what my children are going to eat for lunch, that would mean that even if my girls know that I'm eating some toast for lunch, that has no impact on their decision of what to eat for lunch. Okay, so it's saying that the chance for one person or another person that the events are independent. And so in probability terms, this first one, what this first one here is talking about, it's saying the chance of event A, so the probability of Miss Sneddon having toast for lunch, that is the same as the chance of Miss Sneddon having toast for lunch knowing that her daughter is not having toast for lunch. So the conditional probability, so given some new information, has that changed the probability? And if they're independent, then that won't change that probability at all. And so if I told you the probability of A, of having toast, is 0.5, and the probability of having toast, knowing that my child is going to have toast, if that probability is 0.3, then I can say that is the, in order to be independent, those two things must be equivalent. And because this probability does not equal that probability, they would be not independent. So we can argue it both from this formulaic point of view, but more importantly, it's about arguing it from the words, knowing that the chance of this happening given new information, that's changed the probability, therefore that won't be independent anymore. Okay. And if I was to think about it, the second rule that is listed there, that talks about the intersection. And so if I draw a little Venn diagram, probability of A and probability of B, as long as there is no overlap between them, then they are independent events. Okay, having pizza is independent of whether I have a cup of tea. They are independent events. There is no overlap between those probabilities. And that's what that little intersection sign means, is that intersection sign would be if I had a Venn diagram where they overlapped, that means they're not independent, okay, because doing one thing will affect the other. So those are the only formulas that we really need to be aware of, and just more it's that being able to reason and argue why a situation is independent or not. Okay, last little piece is our distributions. So this is, I've tried to summarize what we need to know about our distributions. So normal distribution. This is the one we're probably more of us are familiar with. It has two parameters, mean and standard deviation. And it has this standard normal distribution with a formula that allows us to convert. So I didn't actually write that down. The standard normal distribution has a mean of 0 and a standard deviation of 1. So that's our reference distribution that's useful. Now the other continuous distributions are our triangular and rectangular. And the key idea is area of a triangle, half the base times the height is your area. For rectangle, base times the height. And so those are on your formula sheet. You've got these formula and they're reminding you of what the height is and whatnot for each of these distributions. And you've just got to know height, base, how do I calculate each of those? Then our other distributions are our binomial and our Poisson. And so these are, so the normal, the binomial and Poisson, these are all on our calculators. Okay, so these three are all on our calculator. And that's when we use our, that's when we're going to use our PD mode or our CD mode or our inverse normal mode. I can't spell inverse, INV. So those are our calculator ones. Now, if you're not familiar with those, then let me know and I can do a session going through how to use your calculator to do those ones. There are a couple of extra formulas on our formula sheet, mean and standard deviation. That they sometimes might ask you to calculate the mean and standard deviation of a binomial or Poisson. And again, there's the probability formula, which we try to avoid using most of the time because we can use our calculators for nearly everything we want to do. So those are those ones. And then we've also got our random variables, which is, this is when we do linear combinations of variables. Trying to think when I don't know that these often come up, the random variables. I don't think they often come up in the scholarship ones. It tends to be more the normal, the Poisson and the binomial. Those are the three most common because they're the three distributions that are used most in real life. Triangular and rectangular might come up a little bit, but I would say the normal, binomial, and Poisson, those are the three that actually I see in every year in the exam. And the only other part that we need to remember is the assumptions. They all assume independence. So as soon as it talks about name an assumption, that's the thing you're going to do. You're going to tell me about independence. And then binomial and Poisson have a couple of extra assumptions there that we can talk about if the distribution was not binomial or Poisson. Okay, so I am going to stop that recording for a minute.